In this video, we work another example of a related rates problem. This will be our last example. And we've got a trough. It's 12 feet long. A little bit difficult to see that. There we go. That's a 12. 12 feet long and 3 feet across the top. The ends are isosceles triangles with altitudes of 3 feet. So it's 3 feet here and then 3 feet here. The water is pumped into the tank at a rate of 2 cubic feet per minute. How fast is the water level rising when the depth is 1 foot? And the depth is being represented by h. That's from the diagram in the text. H is the depth or height of the water level in feet. Okay, so we want to know how fast the water level is rising. How fast is a rate of change? So they're asking us in part A, they're asking us for dH/dt when the depth is 1 foot. Depth is being represented by h. And we know that the water is pumped into the tank at 2 cubic feet per minute because of the units. This number of cubic feet and per minute indicate that we're talking about a rate of change of volume with respect to time. So this should be relatively easy to find. First we need to find the volume of the water in the tank, and then we will find that volume, that equation for volume of the water in the tank in terms of that height h. And then once we know that, we can take the derivative of both sides implicitly with respect to time to find the relationship between the rate of change of volume with respect to time and the rate of change of that water level, that depth or height of the water with respect to time. And then we'll substitute in h equals 1. Okay, well, how do I find the volume of something like this? Well, it's relatively easy. It's a rectangle on top. So really, we just need to take the area of this little triangle at the end and multiply that area by the depth, because that depth is a constant 12 feet. So we have volume is going to be the area of the triangle, a triangular base. I don't want to use depth. I'll just use times the length of the tank. Or they're calling it a trough rather than a tank. So we'll call it the length of the trough. The length is 12 feet. And that's always 12. It doesn't change. But the height changes, the area of the base changes. Well, we can use similar triangles to infer what the area of this is. This is 3 feet across when this is 3 feet high. So the height and the base for this triangle are the same. They're both equal to 3. So if the height of the water level here, or the depth of the water level is h, then we can assume that the base is also h. So the area of a triangle is 1/2 base times height. So it's going to be 1/2 of this distance times this distance, but those distances are the same. This is 3 and that's 3. So this will be h when that's h. They're similar triangles. So we're going to have 1/2 h times h, or h squared, times that 12. It's giving us 6h squared. H is in feet. This is 12 feet. So we're going to have 6h squared cubic feet as our volume. Okay, so we know that that's true. We know that volume and the height are related in this way. And we're asked, how fast is the water level rising when the depth is 1 foot? So we want dH/dt. It's easy enough to find dH/dt by just differentiating both sides of this with respect to time. dV/dt is the derivative of 6h squared with respect to time. So that'll be 6 times 2 is 12 times h to the 1 less power, which is 1, times the derivative of h with respect to time. And we're looking for dH/dt. So we get dH/dt by itself by dividing both sides by 12h. So dH dt is dV dt divided by 12H. And that dV dt is 2 cubic feet per minute, and 12H, I hope that that's square feet. I think it is. H is in feet, and that 12 is also in feet. It's going to be 12 times 1 foot, and these 12 is also in feet. So we have 12 square feet in the denominator. So you have 1/6 of a foot per minute. And if you're saying, how do you know that that's feet? That's because this 12 was also in feet. This is 12 feet times the 1/2 is giving us 6 feet times h squared. When we differentiate, we get 6 feet times 2h. So 6, that gives us the 12 feet times h feet to give us the 12 h feet squared. Okay, so dH dt is 1/6. Well, what does that mean? Well, it just means that when the height of the water level is 1 foot, if our volume of water is being added, or if water is being added at 12 cubic feet per minute, when the height is 1 foot, the rate of change of the height is 1/6 of a foot per minute. So 1 minute later, it will be 1/6 of a foot higher than it is right then. Now for part B, I want to do pretty much the same thing. It says water is rising at a rate of 3/8 of an inch per minute. So dH dt is 3/8 of an inch. Water is rising at a rate of 3/8 of an inch per minute when height is equal to 2 feet. Notice we've got inches and feet, so we're going to have to do some conversions there. Determine the rate at which water is being pumped into the trough. The rate at which water is being pumped into the trough. It doesn't tell you that we're looking for volume, but we know that this time we're looking for volume because this time we're given that the water is rising at a particular rate. So that means we're talking about the change in height of the water level with respect to time. And now our height is in inches rather than feet, but we're still talking about a distance per minute. When they ask us to determine the rate at which the water is being pumped into the trough, that means they're asking for dV dt. So we can't assume that dV dt is still this 2 cubic feet per minute. Now I'm going to use the same equation that we used before. We already know that dV dt is 12H times dH dt. We just need to have the correct units. Now, dH dt is 3/8 of an inch per minute, but I don't want, so that means in 8 minutes, the height actually increases by 3 inches, but I want everything in feet, not in inches. So I want to convert from inches into feet. I know that 1 foot is 12 inches. So multiplying by that doesn't change the value of the fraction at all. It just changes the units that we're measuring everything in. The inches reduce, and we end up with 3 feet divided by this 8 times 12. Actually, it's simpler if I divide 3 goes into 12 4 times. So I have 1 foot in 32 minutes. Oops, I wrote feet. So that height is increasing at increasing by 1 foot for every 32 minutes. Okay, so we know that that's true when h equals 2 feet. So we know what the height is, we know what dH dt is, and we want to know what dV dt is. So we just substitute dV dt is equal to 12h times dH dt. H is equal to 2 feet. dH dt is equal to 1 divided by 32 feet per minute. So we get 12 times 2 times 1 divided by 32. And this is feet times feet times feet per minute. So we end up with cubic feet per minute, which is what we want. And 2 goes into 32 16 times, 2 goes into 12 6 times, and into 6 8 times, or into 16 8 times. And you can divide by 2 again to get 3 there and 4 there. So you end up with 3/4 of a cubic foot per minute, or 0.75 cubic feet per minute. So that's relatively easy. We just use the same formula as before, the one we had already derived, and we use our new information. But it is a little bit tricky in the sense that this time we're asked for dV/dt. It's implied that we're looking for dV/dt, and the picture suggests that we already know dV/dt. So you might be thinking, I can't do that. I already know what dV/dt is. Well, you just have to remember when the authors came up with this problem statement, yeah, maybe they didn't have that on their picture initially. But yeah, so that's our change in volume with respect to time. If we add water at 0.75 cubic feet per minute, then the water level will be increasing at 3/8 of an inch per minute, or 0.375 inches per minute, 0.375 inches per minute when the height is 2 feet.